Imagine you have an identical twin. You both synchronize your watches, share a goodbye hug, and then you board a spacecraft capable of traveling at 90% the speed of light. You journey to Proxima Centauri, our nearest star, and immediately turn around to come home. The round trip takes you about 10 years by your watch. But when you land back on Earth and reunite with your twin, something impossible has happened. Your twin has aged 22 years while you've aged only 10. You're now 12 years younger than your identical twin. This is time dilation, one of the universe's most mind-bending truths that Einstein discovered over a century ago. If you're curious about these cosmic mysteries, make sure to subscribe to this channel and give a thumbs up. Your support means a lot to me. Now let's begin. Time dilation isn't just a theoretical concept studied in physics classrooms. It's happening all around us, every second of every day. The GPS satellites orbiting Earth experience time differently than we do on the surface. Astronauts on the International Space Station age slightly slower than people on Earth. Even walking across the room causes an infinitesimally small but real difference in how you experience time compared to someone sitting still. The faster you move through space, the slower you move through time. This phenomenon reveals something profound about the nature of reality. Time isn't the universal, unchanging backdrop we intuitively believe it to be. Instead, time is flexible, personal, and intimately connected to motion and gravity. Every observer in the universe carries their own personal clock, and these clocks can tick at different rates depending on how fast they're moving or how deep they are in a gravitational field. The story of time dilation begins with a simple thought experiment that Einstein pondered as a young man. What would it be like, he wondered, to ride alongside a beam of light? This seemingly innocent question led to a revolution in physics that overturned centuries of assumptions about space, time, and the nature of reality itself. Before Einstein, everyone believed in absolute time, the idea that there was one universal clock ticking away the same for everyone, everywhere. Newton's physics, which had successfully explained everything from falling apples to planetary orbits, was built on this assumption. Time was time, the same for a farmer in a field as for an astronaut in space, though of course there were no astronauts in Newton's day. But there was a problem brewing in physics. In 1864, James Clerk Maxwell had shown that light was an electromagnetic wave traveling at a specific speed, about 300,000 kilometers per second. But speed relative to what? Sound waves travel through air, water waves through water, but light seemed to travel through empty space. Physicists invented the concept of luminiferous ether, an invisible substance filling all of space through which light waves propagated. The Michelson-Morley experiment in 1887 attempted to detect Earth's motion through this ether by measuring light speed in different directions. If Earth was moving through the ether, light should travel faster in one direction than another, like swimming with or against a current. But the experiment found no difference. Light traveled at the same speed in all directions, regardless of Earth's motion. This null result created a crisis in physics. How could light always travel at the same speed for all observers? If you're on a train moving at 100 kilometers per hour and throw a ball forward at 50 kilometers per hour, someone on the ground sees the ball moving at 150 kilometers per hour. But light didn't follow this common sense rule. Whether you were moving toward a light source or away from it, you always measured the same speed of light. Einstein's genius was to accept this bizarre fact at face value and follow it to its logical conclusions. If the speed of light is constant for all observers, he reasoned, then something else must give. That something else turned out to be time itself. In 1905, at age 26, Einstein published his special theory of relativity. The theory was built on two simple postulates. The laws of physics are the same for all observers moving at constant velocity, and the speed of light in vacuum is the same for all observers. From these two principles, the entire framework of relativistic physics emerges, including time dilation. To understand how motion affects time, let's use one of Einstein's famous thought experiments, the light clock. Imagine a clock made of two mirrors with a photon bouncing between them. Each bounce is one tick of the clock. If the clock is stationary relative to you, the photon travels straight up and down, covering the minimum distance between mirrors. But now imagine this clock is on a fast-moving train passing by you. From your perspective on the platform, the photon doesn't just move up and down, it also moves sideways with the train. This means the photon travels a longer diagonal path between bounces. Since light speed is constant and the photon has to travel a longer distance, more time must pass between ticks. The moving clock runs slower than a stationary one. This isn't an illusion or a mechanical effect, it's how time itself behaves. Any clock on that train, whether it's a light clock, an atomic clock, or a biological clock like your heartbeat, will run slower from the platform observer's perspective. Time itself is dilated, stretched out by motion. The mathematical relationship is beautifully simple. The time dilation factor, often called gamma, equals 1 divided by the square root of 1 minus velocity, squared over the speed of light squared. When velocity is small compared to light speed, gamma is essentially 1, no noticeable time dilation. But as velocity approaches light speed, gamma approaches infinity, meaning time slows to a crawl. At 50% light speed, gamma equals about 1.15. Time passes 15% slower. At 90% light speed, gamma jumps to 2.3. Time passes less than half as fast. At 99% light speed, gamma is 7.1. At 99.9%, it's 22.4. The closer you get to light speed, the more dramatic the effect becomes. But here's where it gets even stranger. From the perspective of someone on the fast-moving train, they're not moving. The platform is moving past them, and due to the symmetry of relativity, they see clocks on the platform running slow. Both observers are correct in their own reference frame. There's no absolute answer to whose clock is really running slower. It depends on your perspective. This reciprocal time dilation seems paradoxical. How can each observer see the other's clock running slow? The resolution comes from understanding that simultaneity, whether two events happen at the same time, is also relative. Events that appear simultaneous to one observer may not be simultaneous to another moving observer. This relativity of simultaneity is key to resolving apparent paradoxes in special relativity. The effects of time dilation have been confirmed by countless experiments. In 1971, physicists Haffley and Keating flew atomic clocks around the world on commercial airliners. When compared to reference clocks on the ground, the flying clocks showed the predicted time dilation. They had aged less than the stationary clocks by exactly the amount Einstein's equations predicted. The twin paradox is perhaps the most famous and controversial thought experiment in all of relativity. It seems to create an impossible situation that challenges our understanding of time dilation. Here's the setup. One twin stays on Earth while the other travels to a distant star at high speed and returns. According to time dilation, the traveling twin ages slower. But wait, from the traveling twin's perspective, isn't Earth the one moving away and then returning? Shouldn't the Earth twin be younger? This apparent contradiction has puzzled students and even some physicists for over a century. The resolution lies in a crucial asymmetry. The traveling twin changes reference frames. They accelerate to high speed, turn around at the distant star, and decelerate upon return. These accelerations break the symmetry between the twins. The traveling twin feels forces during acceleration. They're pushed back into their seat during launch, experience weightlessness during the journey, and feel deceleration forces during the turnaround and landing. The Earth twin feels none of these forces. In the framework of special relativity, we can analyze the twin paradox by carefully tracking what each twin observes. During the outbound journey, each twin sees the other's clock running slow due to time dilation. But during the turnaround, something dramatic happens. From the traveling twin's perspective, the Earth twin's clock suddenly jumps forward, aging years in what seems like moments. This jump in the Earth twin's age, as observed by the traveling twin, accounts for the age difference when they reunite. The twin paradox isn't just theoretical, we see its effects in real cosmic experiments. Cosmic ray muons provide a perfect natural demonstration. Muons are subatomic particles created when cosmic rays strike Earth's upper atmosphere, about 15 kilometers up. These muons have a half-life of only 2.2 microseconds. Even traveling at near light speed, they should decay long before reaching Earth's surface. A muon traveling at 99.9% light speed would only travel about 660 meters before half of them decay. Yet we detect huge numbers of muons at sea level. How do they survive the 15-kilometer journey? Time dilation is the answer. From our perspective, the muons' internal clocks run slow, giving them more time to reach the surface before decaying. From the muons' perspective, length contraction makes the atmosphere appear much thinner, so they have less distance to travel. Both viewpoints give the same result. Muons reach the surface in numbers that would be impossible without relativistic effects. Particle accelerators provide even more dramatic confirmations of time dilation. At CERN's Large Hadron Collider, protons are accelerated to 99.99999% the speed of light. At this speed, the time dilation factor gamma is about 7,000. From our perspective, time for these protons has slowed to a crawl. Unstable particles that would normally decay in nanoseconds can travel around the 27-kilometer ring thousands of times before decaying. The Stanford Linear Accelerator Center conducted an elegant experiment with time dilation using electrons. They accelerated electrons to various speeds and measured the decay rates of unstable particles produced in collisions. The results matched Einstein's predictions perfectly. The faster the particles moved, the slower they decayed, with the time dilation factor following the relativistic formula exactly. But time dilation isn't limited to subatomic particles. The global positioning system provides an everyday example that affects millions of people. GPS satellites orbit Earth at about 14,000 kilometers per hour, fast enough that special relativistic time dilation causes their clocks to run about 7 microseconds per day, slower than Earth clocks. But there's also a general relativistic effect. The satellites experience weaker gravity than we do on the surface, causing their clocks to run about 45 microseconds per day faster. The net effect is that GPS satellite clocks run about 38 microseconds per day faster than Earth clocks. This might seem trivial, but GPS works by precisely timing signals from multiple satellites. Light travels about 300,000 kilometers per second, so a 38 microsecond error would cause position errors of over 11 kilometers per day. Without correcting for both special and general relativistic effects, GPS would be useless for navigation within days. The gravity probe. An experiment in 1976 provided one of the most precise tests of gravitational time dilation. A hydrogen maser clock was launched on a rocket to an altitude of 10,000 kilometers. As predicted by general relativity, the clock's frequency increased as it climbed away from Earth's gravitational field. The measured change agreed with Einstein's predictions to within 70 parts per million, an extraordinary confirmation of the theory. Astronomers have observed time dilation on cosmic scales. When we observe distant supernovae, exploding stars billions of light-years away, we see their light curves stretched by exactly the amount predicted by cosmological time dilation. A supernova that would normally brighten and fade over 20 days appears to take 22 days if it's at a redshift of 0.1. This cosmic time dilation is due to the expansion of space itself stretching the time intervals we observe. Pulsars, rapidly rotating neutron stars that emit regular radio pulses, provide natural clocks for testing relativity. The binary pulsar PSR B191316, discovered by Hulse and Taylor in 1974, consists of two neutron stars orbiting each other. As they orbit, they experience constantly changing gravitational fields and velocities, causing complex time dilation effects. Decades of observations have confirmed these effects to extraordinary precision, earning Hulse and Taylor the 1993 Nobel Prize in Physics. The most extreme time dilation in the universe occurs near black holes. As you approach a black hole's event horizon, gravitational time dilation becomes infinite. From the perspective of a distant observer, your clock would appear to slow down more and more as you approach the horizon, eventually appearing to freeze. You would never be seen crossing the event horizon. Your final moments before crossing would appear to last forever to the outside universe. This effect was dramatically illustrated in the movie Interstellar, where the crew visits a planet orbiting close to a supermassive black hole. Due to the extreme gravitational field, 1 hour on the planet's surface equals 7 years for their colleague waiting in orbit. While Hollywood took some liberties, the basic physics was accurate. Extreme gravity really can create such dramatic time dilation. Recent observations of stars orbiting our galaxy's central black hole, Sagittarius A star, have allowed astronomers to measure gravitational time dilation in this extreme environment. The star S2, which passes within 18 billion kilometers of the 4 million solar mass black hole, experiences measurable time dilation at its closest approach. The gravity instrument on the Very Large Telescope has detected this effect, providing another confirmation of Einstein's theory in the strong field regime. Time dilation also plays a crucial role in our understanding of the early universe. During cosmic inflation, the period of exponential expansion in the first fraction of a second after the Big Bang, different regions of space experience different rates of time flow. This differential time dilation helped create the tiny density fluctuations that eventually grew into galaxies and cosmic structure. The discovery of gravitational waves has opened a new window for studying time dilation. When two black holes spiral together and merge, they create ripples in space-time that stretch and compress space as they pass. LIGO and Virgo detectors have observed dozens of these events, each one confirming that time and space are intimately connected and can be distorted by massive objects and high velocities. To truly understand why moving faster slows time down, we need to dive into the fundamental nature of space-time itself. Einstein's great insight wasn't just that time can dilate, it was that space and time are not separate entities, but different aspects of a four-dimensional fabric called space-time. This unified view explains not only why time dilation occurs, but why it must occur for the universe to make logical sense. Think of space-time as a four-dimensional stage where all events in the universe take place. 3 dimensions are spatial, length, width, and height, and one is temporal. But here's the key insight. Just as you can rotate an object in 3-dimensional space, changing which part points up versus sideways, motion through space is actually a rotation in 4-dimensional spacetime that mixes space and time coordinates. Every object in the universe is always moving through spacetime at exactly the speed of light. Yes, you read that correctly. Even as you sit still reading this, you're moving through spacetime at light speed. The catch is that this motion can be distributed between movement through space and movement through time. When you're at rest relative to something, all your motion is through time. Your clock ticks at its maximum rate. When you move through space, some of that motion is diverted from time to space, so your clock ticks slower. Imagine you're driving north at exactly 100 kilometers per hour. If you turn slightly northeast, you're still going 100 kilometers per hour total, but now you're not making as much northward progress. Some of your speed is directed eastward. Similarly, when you move through space, some of your speed through time is redirected to speed through space. The total speed through space-time always remains constant at the speed of light. This explains why nothing can exceed light speed. You'd need to go faster than your total speed through space-time, which is impossible. It also explains why photons, which travel at light speed through space, don't experience time at all. All their space-time motion is through space, leaving none for time. From a photon's perspective, its emission and absorption happen simultaneously, even if billions of years pass from our perspective. And if you're wondering whether anything in the universe can actually break this cosmic speed limit, I explore that exact question in my video called "Is the speed of light really the fastest speed in the universe?" You'll discover how phenomena like quantum entanglement and cosmic expansion seem to violate light speed while actually confirming Einstein's laws. It perfectly complements what we're discussing about time dilation, showing how these apparent violations actually confirm the deep connection between space, time, and the cosmic speed limit. The link of the video is in the description and on the card above. Now let's continue with how this universal speed limit creates the strange geometry of space-time. The mathematics of this space-time rotation is encoded in the Lorentz transformation, named after Hendrik Lorentz, who derived them before Einstein provided the physical interpretation. These equations tell us exactly how space and time coordinates mix when we change reference frames. Just as rotating an object in space involves sines and cosines, rotating in space-time involves hyperbolic sines and cosines, mathematical functions that describe rotations in spacetime's peculiar geometry. This geometry is called Minkowski spacetime, after Hermann Minkowski, Einstein's former mathematics professor, who reformulated special relativity in geometric terms. In ordinary Euclidean space, the distance between 2 points is given by the Pythagorean theorem. In Minkowski spacetime, the distance between two events, called the spacetime interval, involves subtracting the time component instead of adding it. This minus sign is what makes spacetime geometry fundamentally different from spatial geometry. The spacetime interval between two events is invariant. All observers agree on its value, even if they disagree on the spatial distance and time interval separately. This invariance is the key to understanding relativity. While different observers measure different distances and durations, they all agree on the space-time interval, which represents the true separation between events in four-dimensional space-time. Let's make this concrete with an example. Suppose a firecracker explodes at one location, and then another explodes 1 second later and 300,000 kilometers away. For an observer at rest relative to the firecrackers, the spatial distance is 300,000 kilometers and the time interval is 1 second. But the space-time interval is 0. Because light travels 300,000 kilometers in 1 second, a photon emitted by the first explosion could trigger the second. Now consider a spacecraft traveling at half light speed from the first firecracker to the second. From the spacecraft's perspective, the explosions happen at the same location but at different times. The spatial distance is 0, but there's still a time interval, yet when they calculate the space-time interval, they get the same answer, 0. All observers agree on space-time intervals, even when they disagree on space and time separately. This geometric view reveals why causality is preserved in relativity. Events with time-like separation, where the time interval exceeds the spatial distance divided by light speed, can be causally connected. One can influence the other. Events with space-like separation cannot influence each other without faster-than-light signals. The light cone at each point in spacetime divides events into those that can influence that point, past light cone, and those that can be influenced by it, future light cone. The energy-momentum relation in relativity further illuminates time dilation. Einstein's famous equation E equals mc squared is just the rest energy case. The full relation is E squared equals pc squared plus mc squared squared, where p is momentum. For a particle at rest, momentum is zero, and we get the famous equation. For a photon with no mass, E equals pc. For particles with mass moving at high speed, both terms contribute. As a massive particle accelerates, its momentum and kinetic energy increase without bound as velocity approaches light speed. This is another way to see why massive objects can't reach light speed. It would require infinite energy. The time dilation factor gamma appears naturally in these equations, connecting the dynamics of motion to the geometry of spacetime. Relativistic Doppler shift provides another window into time dilation. When a light source moves toward you, its light is blue shifted to higher frequencies. When it moves away, it's redshifted, but the relativistic formula includes time dilation effects that modify the classical Doppler formula. For sources moving at relativistic speeds, time dilation significantly affects the observed frequency shift. This relativistic Doppler effect has been measured with exquisite precision. In the Ives-Stilwell experiment, hydrogen atoms were accelerated to high speeds, and their light emission was observed from different angles. The frequency shifts matched relativistic predictions perfectly, providing direct evidence that moving clocks run slow. The transverse Doppler effect is particularly interesting. In classical physics, there's no Doppler shift for motion perpendicular to the line of sight. But in relativity, time dilation causes a redshift even for transverse motion. This purely relativistic effect has been confirmed in numerous experiments and is routinely observed in particle physics. Recent experiments have pushed time dilation measurements to extraordinary precision. Optical atomic clocks can now measure time to better than 1 part in 10 to the 18th. That's like measuring the age of the universe to within a second. These clocks are so sensitive they can detect the time dilation from walking speed velocities or from lifting the clock by just 1 centimeter against Earth's gravity. While special relativity revealed that motion through space affects the flow of time, Einstein's general theory of relativity unveiled an even more profound connection. Gravity itself warps time. The stronger the gravitational field, the slower time flows. This gravitational time dilation isn't just an abstract concept, it affects everything, from the GPS in your phone to the evolution of the universe itself. Einstein's journey from special to general relativity began with what he called his happiest thought, the realization that someone falling freely doesn't feel their own weight. If you were in an elevator and the cable snapped, you'd float inside the elevator during the fall, unable to tell whether you were falling in a gravitational field or floating in deep space. This equivalence between free fall and weightlessness led Einstein to a revolutionary idea. Gravity isn't a force, but a curvature of space-time itself. Imagine space-time as a flexible rubber sheet. Place a bowling ball on it, and the sheet curves downward. Roll marbles near the bowling ball and they'll curve toward it, not because of a mysterious force, but because they're following the straightest possible paths on the curved surface. Similarly, massive objects curve spacetime, and this curvature is what we experience as gravity. But here's the crucial point. Massive objects don't just curve space, they curve time as well. The deeper you are in a gravitational field, the slower your clock runs compared to clocks farther away. This isn't because gravity somehow mechanically affects clocks. Time itself flows differently at different gravitational potentials. The mathematical description of gravitational time dilation is elegantly simple for weak fields like Earth's. Time runs slower by a factor of approximately 1 minus gm over rc squared, where g is Newton's gravitational constant, m is the mass creating the field, r is your distance from the center, and c is light speed. Near Earth's surface, clocks run slower by about 1 part in 7 billion compared to clocks far from any gravitational field. This might seem negligible, but modern technology is sensitive enough to measure it. In 1959, Pound and Rebka performed a landmark experiment at Harvard University. They measured the frequency of gamma rays traveling up and down a 22-meter tower. The rays climbing against gravity were redshifted exactly as general relativity predicted, direct proof that time runs slower in stronger gravitational fields. The most precise test of gravitational time dilation used hydrogen masers, extremely stable atomic clocks. In 1976, Gravity Probe A carried a hydrogen maser to an altitude of 10,000 kilometers. Comparing its frequency to identical clocks on Earth revealed gravitational time dilation matching Einstein's predictions to within 0.007%. Today, optical atomic clocks have pushed precision even further. In 2010, researchers at NIST compared two aluminum-ion clocks, one 33 centimeters higher than the other. Even this tiny difference in height, less than the length of your forearm, produced a measurable difference in their tick rates. The higher clock ran faster by 4 parts in 10 to the 17th, exactly as predicted by general relativity. This extreme sensitivity has practical implications. If you live on the top floor of a tall building, you age slightly faster than someone on the ground floor. Over a lifetime, the difference might amount to a few microseconds, negligible for human experience but measurable with precise instruments. Time literally flows at different rates at different heights in Earth's gravitational field. The global positioning system must account for both special and general relativistic effects to maintain accuracy. GPS satellites orbit at 20,000 kilometers altitude, where Earth's gravitational field is weaker. This causes their clocks to run about 45 microseconds per day, faster than Earth's surface clocks due to gravitational time dilation. Combined with the special relativistic slowing of 7 microseconds per day due to orbital motion, the net effect is that satellite clocks run 38 microseconds per day fast. Without relativistic corrections, GPS errors would accumulate at 11 kilometers per day, rendering the system useless within minutes. Every GPS receiver effectively performs relativistic calculations, making Einstein's theories part of daily life for billions of people. Your phone knows your position precisely because it accounts for the warping of time by gravity and motion. Near massive objects, gravitational time dilation becomes extreme. On the surface of a neutron star, gravity is so strong that time runs about 30% slower than far from the star. An hour on the neutron star surface corresponds to about an hour and 25 minutes for a distant observer. The star's surface gravity is 200 billion times stronger than Earth's. You'd weigh as much as a mountain range. Black holes represent the ultimate extreme of gravitational time dilation. As you approach the event horizon, the point of no return, time dilation approaches infinity. From the perspective of a distant observer, your clock appears to slow more and more as you near the horizon, eventually appearing to freeze. You'd never be seen crossing the horizon. Your final moments would appear to last forever to the outside universe. This creates the black hole information paradox. If you fall into a black hole carrying information, That information appears to be frozen at the horizon from the outside perspective, yet you experience crossing the horizon in finite time. This paradox has puzzled physicists for decades and connects to deep questions about quantum gravity and the nature of information. Recent observations have confirmed gravitational time dilation in extreme environments. The star S2 orbits our galaxy's central black hole, passing within 18 billion kilometers at closest approach, about 4 times the distance from Neptune to the Sun. At this distance from a 4 million solar mass black hole, gravitational time dilation is measurable. The gravity instrument detected the gravitational redshift of light from S2, confirming Einstein's predictions in the strong field regime. Gravitational waves provide another confirmation of Einstein's theory. When two black holes spiral together, they create ripples in spacetime that propagate outward at light speed. These waves stretch and compress space and time as they pass. LIGO and Virgo detectors have observed dozens of black hole mergers, each one confirming that massive objects warp spacetime exactly as general relativity predicts. The cosmic implications of gravitational time dilation are profound. In the early universe, when matter was much denser, gravitational time dilation was more significant. Different regions experienced different rates of time flow depending on local density variations. This differential time dilation influenced how structures formed, contributing to the cosmic web of galaxies we see today. Even more dramatically, some theories suggest our entire universe might exist inside a black hole in a higher dimensional space. If true, we'd all be experiencing extreme gravitational time dilation relative to that external universe. What seems like billions of years to us might be moments in the external frame. A mind-bending possibility that illustrates how gravitational time dilation could operate on the largest possible scales. When we venture into the quantum world, time dilation becomes even stranger. At the smallest scales of reality, where particles exist in superpositions and can be entangled across vast distances, time itself seems to follow different rules. Recent experiments have shown that quantum systems can experience superpositions of different time dilations, and that time might even be an emergent property rather than fundamental to reality. The intersection of quantum mechanics and relativity has puzzled physicists since both theories were developed. Quantum mechanics describes a world of probabilities and instantaneous wave function collapse, while relativity insists that nothing, including information, can travel faster than light. When we add time dilation to the mix, paradoxes multiply. How does a quantum superposition evolve when different parts experience different rates of time? Can quantum entanglement survive when entangled particles move at relativistic speeds? Recent experiments have begun answering these questions. In 2017, researchers at the University of Vienna demonstrated that single photons can experience quantum superposition of different time dilations. They sent photons through an interferometer where different paths experience different gravitational fields, simulated by careful phase adjustments. The photons remained in superposition, experiencing multiple time dilations simultaneously until measured. This has profound implications. If a quantum system can be in a superposition of different time dilations, then time itself becomes quantum mechanical at fundamental scales. A particle might not have a definite age, but rather exist in a superposition of ages. This quantum time dilation could affect everything from quantum computing to our understanding of black hole evaporation. The quantum Zeno effect provides another window into time's quantum nature. By measuring a quantum system frequently enough, you can freeze its evolution, essentially stopping time for that system. In 2015, researchers at Cornell demonstrated this by repeatedly measuring atoms, preventing them from tunneling between energy states. The measurement itself altered the flow of time for the quantum system. Even more bizarrely, the quantum anti-Zeno effect shows that certain measurements can accelerate a system's evolution, making time flow faster for it. The act of observation doesn't just reveal reality, it shapes how time flows for quantum systems. This suggests that time might not be a fixed backdrop, but something that emerges from quantum interactions. Quantum tunneling presents another time dilation puzzle. When particles tunnel through barriers they classically couldn't cross, how long does it take? Recent experiments using attosecond lasers, producing pulses lasting 10 to the negative 18 seconds, have shown that tunneling might be instantaneous. Particles appear on the other side of barriers without any time passing, as if they temporarily step outside normal spacetime. In 2020, researchers at the University of Toronto measured tunneling times for atoms passing through optical barriers. Using ultra-precise atomic clocks, they found the tunneling time was consistent with zero. The atoms crossed the barrier instantaneously. This suggests that during tunneling, particles might experience infinite time dilation, freezing their internal clocks. Quantum field theory adds another layer of complexity. In this framework, particles are excitations in quantum fields that fill all of spacetime. These fields fluctuate constantly, creating virtual particle pairs that pop into existence and annihilate in times shorter than the Heisenberg uncertainty principle allows us to measure. Do these virtual particles experience time dilation? The question challenges our understanding of what time means at the quantum scale. The Unruh effect predicts that accelerating observers see empty space filled with a warm bath of particles. From the perspective of an accelerating observer, the vacuum isn't empty but contains real particles with real temperatures. Since acceleration and gravity are equivalent according to Einstein's equivalence principle, this suggests that gravitational time dilation might have quantum origins. Recent proposals suggest testing this by accelerating atoms to extreme speeds and measuring their internal quantum states. If the Unruh effect is real, accelerated atoms should thermalize with the quantum vacuum, experiencing time differently than predicted by classical relativity alone. These experiments push the boundaries of our technological capabilities, but might reveal how quantum mechanics and time dilation truly interact. Quantum entanglement raises fascinating questions about time dilation. If two entangled particles are separated and one is accelerated to relativistic speeds, what happens to their entanglement? Experiments have shown that entanglement survives but becomes degraded in a specific way predicted by relativistic quantum mechanics. The moving particles' reduced time flow affects the quantum correlations, but doesn't destroy them entirely. In 2019, researchers demonstrated this using entangled photons, with one photon traveling through moving glass to simulate relativistic motion. The entanglement survived but showed signatures of the simulated time dilation. This has implications for quantum communication with spacecraft and might even provide a way to measure time dilation using quantum correlations. The black hole information paradox connects quantum mechanics and gravitational time dilation in the most extreme way. As matter falls toward a black hole, it experiences increasing time dilation. From the outside perspective, information appears frozen at the horizon, but Hawking radiation suggests black holes evaporate, potentially destroying the information. Recent theories like the holographic principle and firewall hypothesis attempt to resolve this by reconsidering how quantum information behaves in extreme gravitational time dilation. Quantum gravity theories like loop quantum gravity suggest spacetime itself is quantized at the Planck scale, about 10 to the negative 35 meters. At this scale, time might not flow continuously, but in discrete jumps of about 10 to the negative 43 seconds, the Planck time. This would mean time dilation isn't perfectly smooth, but occurs in tiny quantum jumps, too small for current technology to detect. String theory offers another perspective. suggesting that what we perceive as time might emerge from more fundamental processes in higher dimensions. In some string theory models, time dilation arises from the way strings vibrate differently in curved spacetime. The familiar smooth time of general relativity would be an approximation that breaks down at quantum scales. Recent work on quantum reference frames has shown that time itself might be relative in quantum mechanics, just as position and momentum are. Different quantum observers might disagree not just on when events occur, but on the order of events. This quantum temporal uncertainty adds to relativistic time dilation, creating a rich structure where time becomes increasingly ambiguous at small scales. The delayed choice quantum eraser experiment demonstrates that quantum effects can seem to reach backward in time. By choosing whether to measure certain quantum properties after a particle has passed through a double slit, experimenters can retroactively determine whether the particle went through one slit or both. While this doesn't violate causality, it shows that time in quantum mechanics doesn't flow the way our intuition suggests. The universe provides natural laboratories where time dilation reaches extremes far beyond anything we can create on Earth. From the surfaces of neutron stars to the jets of quasars, from the edge of black holes to the accelerating expansion of space itself, cosmic phenomena push time dilation to its absolute limits. These extreme environments don't just confirm Einstein's theories, they reveal new aspects of how time behaves under conditions that challenge our understanding of physics. Neutron stars are among the most extreme objects in the universe that we can still observe directly. These city-sized remnants of supernovae pack more than the Sun's mass into a sphere just 20 kilometers across. The surface gravity is 200 billion times stronger than Earth's, creating gravitational time dilation so severe that 1 hour on the surface equals about 1 hour and 25 minutes for a distant observer. But the time dilation on a neutron star isn't uniform. These objects spin at incredible rates, some rotating over 700 times per second. At the equator of such a rapidly spinning neutron star, the surface moves at a significant fraction of light speed, adding special relativistic time dilation to the gravitational effect. The combination creates complex patterns where time flows at different rates across the star's surface. Pulsar timing has revealed these effects with extraordinary precision. PSR J07373039, a double pulsar system where two neutron stars orbit each other, provides a perfect laboratory for studying extreme time dilation. The pulsar's regular radio pulses act like precise clocks, allowing astronomers to measure relativistic effects to better than 1 part in a million. The system shows periastron advance, similar to Mercury's perihelion precession but much stronger, frame dragging and time dilation effects that match general relativity's predictions perfectly. Even more extreme are magnetars, neutron stars with magnetic fields a quadrillion times stronger than Earth's. These fields are so intense they distort spacetime itself, creating additional time dilation effects. The magnetic field energy density becomes comparable to the mass energy density, warping spacetime in ways that go beyond simple gravitational effects. Near a magnetar's surface, atoms are stretched into needle-like shapes, and time itself flows differently depending on orientation relative to the magnetic field. Black holes represent the ultimate extreme of gravitational time dilation. The event horizon marks the boundary where time dilation becomes infinite from an outside observer's perspective. But the approach to this boundary reveals fascinating physics. As matter spirals toward a black hole in an accretion disk, it experiences gradually increasing time dilation. The inner edge of the disk just outside the event horizon experiences such extreme time dilation that processes that would take seconds in normal space appear to take hours to outside observers. This has observable consequences. X-ray observations of black hole accretion disks show quasi-periodic oscillations. regular brightness variations that may represent the orbital period of hotspots in the inner disk. These oscillations are affected by both gravitational and special relativistic time dilation, as the material orbits at a significant fraction of light speed in an extreme gravitational field. The frequency of these oscillations tells us about the space-time geometry near the black hole. The merger of black holes creates even more extreme time dilation effects. As two black holes spiral together, they create a dynamically changing gravitational field where time dilation varies rapidly in both space and time. LIGO and Virgo have detected gravitational waves from dozens of these mergers, each one confirming that time behaves exactly as Einstein predicted, even in these most violent cosmic events. During the final milliseconds before merger, the black holes orbit each other at speeds approaching half the speed of light. The combination of extreme gravity and high velocity creates time dilation effects so severe that what appears as milliseconds to us would be experienced very differently by any observer near the merging holes. The gravitational waves themselves encode information about how time flows in these extreme conditions. Active galactic nuclei, supermassive black holes feeding on surrounding matter, create jets that shoot out at over 99% light speed. These jets experience extreme special relativistic time dilation. From our perspective, particles in these jets age very slowly, allowing unstable particles to travel millions of light-years before decaying. From the jet's perspective, the universe appears length contracted, making intergalactic journeys seem much shorter. The apparent superluminal motion observed in some jets is a direct consequence of time dilation combined with projection effects. When a jet travels at 99% light speed at a small angle to our line of sight, it appears to move across the sky at several times light speed. This isn't true faster than light motion, but rather a consequence of how time dilation and light travel time combine when observing relativistic motion. Gamma-ray bursts, the most energetic explosions in the universe, accelerate particles to speeds where the Lorentz factor, gamma, exceeds 1000. At these speeds, time dilation is so extreme that 1 second in the particle's frame equals over 15 minutes in our frame. This explains how gamma-ray bursts can maintain coherent jets over vast distances. From the particle's perspective, they haven't traveled very far at all. The cosmological implications of time dilation are equally profound. As we look at distant galaxies, we're seeing them not just as they were in the past, but also experiencing cosmological time dilation. The expansion of space stretches time intervals, making distant supernovae appear to evolve in slow motion. A supernova at redshift z equals 1 appears to brighten and fade twice as slowly as a nearby supernova. This cosmological time dilation has been measured precisely using Type Ia supernovae as standard candles. The time dilation matches exactly what we expect from an expanding universe, providing independent confirmation of cosmic expansion beyond just the redshift of light. It's one of the strongest pieces of evidence that the universe really is expanding rather than light just losing energy over cosmic distances. The cosmic microwave background radiation itself is affected by gravitational time dilation. Photons climbing out of gravitational wells are redshifted, the Sachs-Wolf effect, while those falling into wells are blueshifted. As the universe evolved and structures formed, these effects left imprints in the CMB that we can observe today. The patterns tell us how time flowed differently in different regions of the early universe. Dark energy adds another layer to cosmic time dilation. As the universe's expansion accelerates, the time dilation between us and distant galaxies increases faster than it would in a non-accelerating universe. In the far future, this will become extreme. Galaxies will be redshifted so severely that their time will appear nearly frozen from our perspective before they disappear beyond the cosmic horizon entirely. Some of the most extreme time dilation might occur in hypothetical objects like white holes, time-reversed black holes, or in the quantum foam at the Planck scale. While these remain theoretical, they suggest that time dilation might have no upper limit. Time could be dilated arbitrarily close to stopping completely under the right conditions. The story of how humanity confirmed time dilation through increasingly sophisticated experiments is a testament to human ingenuity and our ability to test nature's most counterintuitive predictions. From the first crude tests in the early 20th century to today's atomic clocks that can measure time to 18 decimal places, each experimental confirmation has not only validated Einstein's theories, but also opened new technological possibilities that shape our modern world. The first experimental hint of time dilation came even before Einstein's theory, though it wasn't recognized as such at the time. In 1887, the Michelson-Morley experiment failed to detect Earth's motion through the hypothetical ether, suggesting that light speed was constant regardless of motion. This null result was actually the first experimental evidence that would eventually lead to special relativity and time dilation. The earliest direct test of time dilation came from observing cosmic ray muons in 1941. Bruno Rossi and David Hall at the University of Chicago detected muons at sea level that shouldn't have survived the journey from the upper atmosphere where they're created. The only explanation was time dilation. The muons' high speed slowed their internal clocks, giving them more time to reach Earth's surface before decaying. But the most dramatic early confirmation came from the Haffel-Keating experiment in 1971. Joseph Haffel and Richard Keating flew cesium atomic clocks around the world on commercial airliners, comparing them to reference clocks at the US Naval Observatory. The flying clocks gained 59 nanoseconds flying eastward and lost 273 nanoseconds flying westward, matching relativistic predictions within experimental error. This experiment was remarkable not just for confirming time dilation, but for demonstrating that the effect was measurable with 1970s technology. The atomic clocks of that era were room-sized devices requiring careful temperature control. Today's atomic clocks are thousands of times more precise and can fit on a chip, enabling applications the experimenters could never have imagined. The global positioning system became operational in 1978, turning time dilation from an exotic physics phenomenon into an everyday necessity. Each GPS satellite carries atomic clocks that must account for both special relativistic slowing, 7 microseconds per day, and general relativistic speeding, 45 microseconds per day. Without these corrections, GPS positions would drift by 11 kilometers per day. Modern optical atomic clocks have pushed precision to extraordinary levels. The NIST F2 cesium fountain clock, America's primary time standard, is accurate to 1 second in 300 million years, but optical clocks using strontium or ytterbium atoms are even better, reaching accuracies of 1 second in 15 billion years, more precise than the age of the universe. These ultra-precise clocks have enabled new tests of relativity. In 2018, researchers at Gila used strontium optical clocks to measure gravitational time dilation from a height difference of just 1 millimeter. They could detect the difference in Earth's gravitational field over the width of a human hair. This precision opens possibilities for using time dilation to map gravitational fields and detect underground resources. Particle accelerators provide another arena for testing time dilation. At Fermilab's Tevatron, protons were accelerated to 99.9995% light speed, experiencing time dilation factors over 1,000. Unstable particles that would normally decay in nanoseconds survived for microseconds in the accelerator, traveling hundreds of meters instead of fractions of a millimeter. The Large Hadron Collider pushes even further, accelerating protons to 99.999991% light speed. At this velocity, the time dilation factor exceeds 7,000. From the proton's perspective, the 27-kilometer ring appears contracted to less than 4 meters, and a complete orbit takes microseconds rather than milliseconds. Modern experiments have tested exotic aspects of time dilation. The gravitational redshift of light climbing out of Earth's gravity well has been measured using hydrogen masers on rockets, gamma rays in towers, and even using the Mossbauer effect with iron-57 nuclei. Every test confirms Einstein's predictions to the limit of experimental precision. Quantum experiments have pushed into new regimes. In 2014, researchers demonstrated that single neutrons could be put into superposition states experiencing different gravitational fields, effectively experiencing quantum superposition of different time dilations. This opens the possibility of using quantum systems as ultra-sensitive probes of gravitational fields and time dilation. The technological applications of time dilation extend far beyond GPS. Satellite communications must account for time dilation to maintain synchronization. Financial networks that depend on microsecond timing precision must consider relativistic effects when synchronizing between ground stations and satellites. Even Internet time protocols must account for relativistic effects to maintain global synchronization. Future technologies will leverage time dilation even more directly. Relativistic spacecraft, if we ever build them, will use time dilation as a feature, not a bug. A journey to Proxima Centauri at 99% light speed would take over 4 years from Earth's perspective, but only 7 months from the traveler's perspective. Time dilation becomes a way to make interstellar travel survivable for human crews. Some physicists have proposed using gravitational time dilation for technological applications. Clocks placed in regions of different gravitational potential could serve as gravitational wave detectors, sensing the passing waves through their changing relative rates. Arrays of such clocks could map gravitational fields with unprecedented precision, potentially detecting dark matter or testing modifications to general relativity. The most precise tests of time dilation may come from space-based experiments. The proposed atomic clock ensemble in space, ACES, will place ultra-stable atomic clocks on the International Space Station, comparing them with ground clocks to test Einstein's theories at unprecedented precision. These tests might reveal tiny deviations from general relativity that could point toward quantum gravity theories. Pulsar timing arrays use millisecond pulsars as cosmic clocks to detect gravitational waves with wavelengths of light years. These arrays must account for complex time dilation effects as Earth moves through the solar system's gravitational field and as gravitational waves stretch and compress spacetime. The precision required pushes our understanding of time dilation to its limits. Future quantum networks might use time dilation as a resource. Quantum information protocols that depend on precise timing could leverage relativistic effects to process information in novel ways. Some theorists have proposed that time dilation could be used to protect quantum information from decoherence, preserving quantum states by literally slowing down time for them. Time dilation doesn't just slow down clocks, it opens the theoretical possibility of time travel. While we typically think of time travel as science fiction, relativity shows that we're all time travelers moving into the future at 1 second per second. But time dilation allows for more dramatic possibilities, traveling to the future faster than normal and under certain exotic conditions, perhaps even traveling to the past. These possibilities raise profound questions about causality, free will, and the nature of time itself. If you're fascinated by the real science behind time travel and want to dive even deeper into the possibilities that Einstein's theories open up, I highly recommend the book called Time Travel in Einstein's Universe by J. Richard Gott. It's a fantastic read that explores the physical possibilities of time travel, from wormholes to cosmic strings, all grounded in real physics. The link is in the description and pinned on the comments. Forward time travel through time dilation is not only possible, but routine. Every astronaut who's been to space has traveled slightly into the future relative to Earth. Cosmonaut Gennady Padalka holds the record, having spent 879 days in space over 5 missions. Due to the ISS's orbital velocity, he's aged about 20 milliseconds less than he would have on Earth. He's literally 20 milliseconds in Earth's future. But we could do much better with current technology. A spacecraft accelerating at 1g, Earth's surface gravity, continuously could reach 99% light speed in about 7 years ship time. A round trip to the galactic center at this acceleration would take about 40 years ship time, but 60,000 years would pass on Earth. The travelers would return to an unrecognizable future Earth, the ultimate one-way time travel. This asymmetric aging isn't science fiction, it's an unavoidable consequence of the geometry of space-time. The twin paradox we discussed earlier demonstrates this perfectly. The traveling twin follows a different path through space-time than the Earth twin, and these different paths have different lengths in 4-dimensional space-time. Just as 2 different routes between cities have different distances, different paths through space-time have different proper times. But what about traveling backward in time? This is where things get weird and controversial. General relativity actually permits several scenarios that could enable backward time travel, though each comes with serious caveats and probably insurmountable practical challenges. Rotating black holes, described by the Kerr metric, have a region called the ergosphere, where space-time itself is dragged around the black hole. Inside the ergosphere, it's impossible to remain stationary relative to distant stars. Space-time itself is rotating. Some solutions to Einstein's equations suggest that carefully crafted trajectories through the ergosphere could create closed time-like curves, paths through space-time that loop back to their own past. The Alcubierre warp drive, while designed for faster-than-light travel, could theoretically be configured to create closed time-like curves. By warping space-time in just the right way, you could return to your starting point in both space and time. However, this requires exotic matter with negative energy density, which probably doesn't exist in the required quantities. Traversable wormholes, if they exist, could connect different regions of space-time, potentially including different times. By traveling through a wormhole and returning through normal space at high speed, time dilation could result in arriving before you left. This is the scenario used in many science fiction stories, but it requires exotic matter to keep the wormhole open and may be fundamentally unstable. The cylinder of rotating dust proposed by Frank Tipler is a theoretical construct where an infinitely long, rotating cylinder of matter could create closed, time-like curves around it. While mathematically valid in general relativity, it requires infinite length and may be unstable to small perturbations. No finite version has been shown to enable time travel. But even if these exotic scenarios are possible, they all face the grandfather paradox. What happens if you travel back and prevent your own birth? Various solutions have been proposed. The Novikov self-consistency principle suggests that any actions taken by a time traveler were always part of history. You can't change the past because your time travel was already part of what happened. The multiple timelines interpretation suggests that traveling to the past creates or shifts you to an alternate timeline, avoiding paradoxes by ensuring you can't affect your own past. This connects to the many worlds interpretation of quantum mechanics, where every quantum event splits reality into multiple branches. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics somehow prevent closed, time-like curves from forming. Whenever conditions might allow time travel, quantum effects or other phenomena intervene to prevent it. The universe, in effect, protects itself from paradoxes. Recent research in quantum mechanics has added new perspectives on time travel paradoxes. In 2020, physicists showed that quantum mechanics could resolve the grandfather paradox through quantum superposition. A quantum time traveler could exist in the superposition of having and not having prevented their grandfather's birth, maintaining consistency through quantum uncertainty. The psychological arrow of time presents another puzzle. We remember the past but not the future, and this asymmetry seems fundamental to consciousness. If time travel to the past were possible, would we suddenly remember the future? Would causality still make sense? These questions touch on deep issues in physics, philosophy, and neuroscience. Time dilation also raises questions about the nature of now. In special relativity, simultaneity is relative. Events that are simultaneous for one observer may not be for another. This suggests that past, present, and future all exist equally in four-dimensional spacetime, a view called eternalism or the block universe. If true, time travel might just be an unusual movement through an already existing four-dimensional structure. The alternative presentist view holds that only the present moment exists, with the past gone and the future not yet real. This seems to match our experience but is harder to reconcile with relativity. Time dilation shows that there's no universal now, challenging presentist intuitions about time's nature. Some physicists have proposed that time itself might be emergent rather than fundamental. In this view, time arises from more basic processes, perhaps quantum entanglement or thermodynamic arrow of increasing entropy. Time dilation would then reflect how these underlying processes change with motion and gravity. The black hole information paradox connects time dilation to fundamental questions about information conservation. As matter falls toward a black hole, extreme time dilation appears to freeze it at the horizon from outside perspectives. But if the black hole evaporates through Hawking radiation, what happens to that information? This paradox has driven decades of research into quantum gravity. Recent proposals like the ER-EPR correspondence suggest that quantum entanglement and wormholes might be related, potentially connecting time dilation to quantum mechanics in unexpected ways. If entangled particles are connected by tiny wormholes, time dilation effects could propagate through quantum correlations. Time dilation isn't just a physical phenomenon affecting clocks and particles, it has profound implications for life, consciousness, and our understanding of existence itself. If humans ever travel at relativistic speeds or live near massive objects, time dilation will fundamentally alter the human experience. But even more deeply, time dilation challenges our basic assumptions about identity, mortality, and what it means to exist in time. Let's start with the biological implications. Every cell in your body is a clock, with circadian rhythms governing everything from hormone release to cell division. Your DNA replication, protein synthesis, and neural firing all happen at specific rates. What happens to these biological processes under time dilation? Would a person experiencing significant time dilation age normally from their perspective while appearing to age slowly to outside observers? The answer is yes. Biological processes would slow down exactly like any other physical process. A traveler on a relativistic spacecraft would age normally from their own perspective. Their heart would beat at its usual rate, thoughts would flow at normal speed, and they'd experience hunger and sleep cycles as usual. But relative to Earth, all these processes would be slowed They would literally age more slowly, not just appear to. This has been confirmed with living organisms. Scientists have sent bacteria and other microorganisms on high-speed centrifuges and observed their metabolic rates. While the accelerations required to produce measurable effects are extreme, the results confirm that biological processes obey relativistic time dilation just like physical clocks. But the implications go deeper. Consider identical twins where one travels to a distant star at near light speed. When the traveler returns, they might be decades younger than their earthbound twin. They would have different amounts of lived experience, different numbers of heartbeats, different quantities of thoughts and dreams. Which twin is older in a meaningful sense? The question challenges our concepts of age and identity. Memory and consciousness add another layer of complexity. If you traveled at 99.9% light speed to a star 40 light-years away, the round trip would take just 3.6 years from your perspective, but 80 years would pass on Earth. You'd return with less than 4 years of memories to a world that had experienced 8 decades of history. Your friends would be elderly or dead, your culture transformed, yet you'd feel like you just left yesterday. This temporal displacement would create unprecedented psychological challenges. Returning space travelers would be temporal exiles, disconnected from the flow of history. They'd be living artifacts from the past, with memories of a world that no longer exists. The psychological impact could be more challenging than the physical journey itself. Evolution presents another fascinating consideration. If parts of humanity travel at relativistic speeds while others remain on Earth, we could see divergent evolution. The space travelers would accumulate fewer generations over the same Earth time, potentially evolving more slowly. After millions of years, the two populations might become distinct species, separated not by distance, but by time dilation. Time dilation also affects reproduction and heredity. A relativistic traveler returning to Earth would find that many more generations had passed on Earth. Their children, if they had any before leaving, would be older than them. The normal flow of generations would be disrupted, creating family trees that loop back on themselves temporally. The philosophical implications are even more profound. Time dilation challenges our intuitive notion that time is universal and absolute. If different observers experience fundamentally different amounts of time, what does it mean to exist at the same time as someone else? The concept of simultaneity, so basic to human experience, becomes relative and observer-dependent. This relativity of simultaneity has deep implications for free will and determinism. In relativity, the future already exists in four-dimensional spacetime. It's just as real as the past, we just haven't experienced it yet. This block universe view suggests a deterministic cosmos where the future is fixed, challenging notions of free will and moral responsibility. But quantum mechanics adds uncertainty back into the picture. Even in a relativistic universe, quantum indeterminacy means the future isn't completely determined. The interplay between relativistic time dilation and quantum uncertainty creates a complex picture where neither pure determinism nor pure free will seems correct. The meaning of death becomes complicated under extreme time dilation. If someone falls into a black hole, they experience a finite time before reaching the singularity. But from outside perspectives, they never quite cross the event horizon, their final moments stretched to infinity. Are they dead or alive? The answer depends on your reference frame, challenging binary notions of existence. Consciousness itself might be affected by time dilation in ways we don't yet understand. Some theories suggest consciousness arises from integrated information processing in the brain. Under time dilation, this information processing would slow down relative to outside observers. Would consciousness feel different? Would thoughts and experiences have the same qualitative character? The anthropic principle, The observation that the universe's properties allow for our existence takes on new dimensions with time dilation. We exist at a particular cosmic epoch when stars still shine and galaxies are visible. Beings in the far future, after extreme cosmic expansion and time dilation, would experience a fundamentally different universe. Our temporal position is as important as our spatial position for our existence. Religious and spiritual perspectives must also grapple with time dilation. If souls exist and survive bodily death, how do they experience time? Do they follow the reference frame of the dying body? These questions push theology to consider relativistic effects that ancient religious texts never anticipated. The ethics of time dilation present novel challenges. If we could slow someone's aging through time dilation, should we? Who decides who gets to travel to the future? If criminals were sent on relativistic journeys as punishment, returning to find everyone they knew dead, would this be cruel and unusual? These questions will become practical concerns if relativistic travel becomes possible. Personal identity across time dilation raises philosophical puzzles. Are you the same person after experiencing extreme time dilation? If your body's atoms have aged less than earthbound atoms, if you have fewer memories and experiences, if everyone you knew is gone, what maintains your identity? The continuity of self becomes problematic when time itself becomes relative. The concept of now becomes especially problematic. You and a distant galaxy don't share a universal now, depending on your relative motion. What you consider now at that galaxy could be millions of years in its past or future. This suggests that now is a local concept, not a cosmic one, challenging our intuitive sense of a shared present moment. The universe itself is the ultimate demonstration of time dilation on cosmic scales. When we look at distant galaxies, we're not just seeing them far away in space, we're seeing them in a fundamentally different temporal state. A galaxy 10 billion light-years away appears to us as it was 10 billion years ago, but due to cosmic expansion, its light is also time-dilated. We see its stellar processes unfolding in slow motion, its supernovae taking longer to fade, its stars aging more slowly from our perspective. This cosmic time dilation has allowed us to piece together the universe's history like cosmic archaeologists. By observing galaxies at different distances and therefore different epochs, we can watch the universe evolve. We see young galaxies still forming their first stars, middle-aged galaxies in their prime of star formation, and old galaxies where star formation has nearly ceased. Time dilation turns the universe into its own history book, but the universe's expansion is accelerating, driven by mysterious dark energy. This acceleration adds another layer of time dilation that will fundamentally alter the cosmos. Distant galaxies are not just moving away, they're accelerating away, and their time dilation relative to us is increasing. Eventually, they'll be receding so fast that their time will appear frozen from our perspective, their light redshifted to invisibility. In about 100 billion years, any civilizations that arise will see a very different universe than we do. The cosmic microwave background will be undetectable, other galaxies will have vanished beyond the horizon, and evidence of the Big Bang will be erased. These future beings won't be able to discover the universe's history the way we have. We live in a special epoch when the universe's story is still readable in the sky. This cosmic perspective makes our current moment precious. We exist at a time when we can still see the universe's past and glimpse its future. We can detect the afterglow of the Big Bang, watch galaxies collide, and measure the universe's acceleration. Time dilation has given us this gift, the ability to see across cosmic time and understand our place in the grand story. But time dilation also shapes our future possibilities. If humanity is to spread among the stars, we'll need to reckon with the temporal isolation it creates. Interstellar colonies will be separated not just by distance, but by time. A message sent between stars will take years or decades to arrive. Travelers between colonies will experience different amounts of time than those who stay behind. Human civilization will fragment temporally as well as spatially. Yet this challenge also offers opportunities. Time dilation could be our key to surviving the vast distances between stars. A journey that would take centuries from Earth's perspective could be survivable for the travelers experiencing only years or decades. Generation ships become unnecessary if we can achieve sufficient velocity. Time dilation transforms interstellar travel from impossible to merely difficult. Consider what this means for human knowledge and culture. Libraries on different worlds will age at different rates. Scientific discoveries made on one planet will take years to reach others, and by the time they arrive, the sending world will have advanced further. Each world will develop its own trajectory through time, creating a rich tapestry of human experiences across space and time. The search for extraterrestrial intelligence takes on new dimensions when we consider time dilation. Alien civilizations might use relativistic travel, causing them to experience time differently than their home worlds. We might detect signals from civilizations that have long since vanished in their own reference frame, but whose messages are still traveling through space. Time dilation means we're not just separated from aliens by space, but potentially by radically different temporal experiences. Some scientists have speculated that advanced civilizations might use time dilation strategically. By accelerating to near light speed, they could effectively travel to the future, waiting out cosmic events or letting the universe evolve to more favorable conditions. Black holes could serve as cosmic time machines, allowing civilizations to orbit close to the event horizon and emerge millions of years in the future. Time dilation also offers a form of cosmic immortality. While we can't stop aging in our own reference frame, we could potentially outlive the stars by traveling at extreme velocities. A traveler, approaching light speed arbitrarily closely, could watch the entire future history of the universe unfold in what feels like a human lifetime. They could witness the last stars forming, the final black holes evaporating, and the universe's ultimate fate. But perhaps the most profound insight from understanding time dilation is how it reveals our deep connection to the cosmos. The same laws that govern time's flow in distant galaxies govern the atoms in our bodies. We're not separate from the universe, we're manifestations of its fundamental laws. When we study time dilation, we're studying ourselves. Every atom in your body has experienced time dilation. The hydrogen in your cells has existed since minutes after the Big Bang, experiencing billions of years of cosmic time. The heavier elements have been through stellar cores where extreme gravity dilated time. These atoms have traveled near light speed in cosmic rays and sat motionless in interstellar clouds. They carry the temporal history of the universe within them. You yourself are experiencing time dilation right now. The Earth orbits the Sun at 30 kilometers per second. The solar system orbits the galaxy at 220 kilometers per second, and the galaxy moves through space at hundreds of kilometers per second more. Relative to the cosmic microwave background, the closest thing to a universal rest frame, you're moving at several hundred kilometers per second. Your time is dilated, if only slightly, relative to the universe's average. This means you're not just in the universe, you're part of its dynamic, relativistic dance. Every motion affects your flow through time. Every gravitational field you experience alters your temporal rate. You're a four-dimensional being extended through time as well as space, your world line tracing a unique path through space-time that will never be exactly repeated. Understanding time dilation changes how we think about existence itself. We're not objects persisting through time, we're processes unfolding in space-time. Our consciousness creates the illusion of moving through time, but in the block universe of relativity, our entire timeline exists as a fixed structure. We're not traveling toward the future. We're already there, experiencing it one moment at a time. This view might seem to rob life of meaning or free will, but it actually makes every moment more precious. Your entire world line through space-time is unique, irreplaceable, and eternal in the four-dimensional sense. The moments you experience don't vanish into the past, they remain fixed in space-time, always existing at their specific coordinates. In this sense, everyone and everything achieves a kind of immortality. As you go forward from this moment, remember that you carry time within you. Your personal clock ticks at its own rate, affected by every motion and every gravitational field. You're not a passive observer of time, you're an active participant in its flow. Your journey through space-time is yours alone, creating a unique temporal perspective that adds to the universe's rich tapestry of experiences. The next time you look at the stars, remember that you're seeing across time as well as space. Those photons have traveled for years, centuries, or eons to reach your eyes, carrying messages from the past. But also remember that you're looking at your extended family. Those stars share your physical laws, your cosmic history, and your fundamental nature. Time dilation doesn't separate us from the cosmos. It reveals our deep integration with it. We are temporal beings in a relativistic universe, each experiencing our own flow of time while participating in the cosmic dance of space, time, matter, and energy. Understanding time dilation doesn't diminish our existence, it elevates it, showing us that we're part of something far grander and more beautiful than our everyday experience suggests. We are the universe experiencing time, and time experiencing itself through us. In the grand symphony of existence, each of us plays a unique temporal note that resonates through the cosmos forever. If you made this far, please consider subscribing and giving a thumbs up. And if you enjoyed this video, I am sure you are going to love this other one at the left side of the screen. Does gravity really travel faster than the speed of light? In this video, learn how gravitational waves, black hole collisions, and neutron star mergers have finally revealed that gravity travels at the same speed as light. Explore how LIGO and Virgo's discoveries confirmed Einstein's predictions, why the speed of gravity preserves causality, and much more. See you there.